Look at this digital forest. Sunlight filters through the canopy and reflects off the water in real time. It looks photorealistic, but is entirely computer-generated. Now, look at this terminal. An AI is writing a story about a detective, mimicking Shakespeare while following a list of complex logical constraints. To make sense of the world, both modern computer graphics and modern AI translate reality into geometry and shoot mathematical rays to see what they hit. For decades, both fields were trapped by the same limitation: sequential processing. Video games used a method called rasterization, which essentially painted 3D scenes line by line. Early AI used recurrent neural networks, which read sentences like a person with a magnifying glass, scanning word 1, then word 2, then word 3. This created a universal bottleneck. Because the system processed things in a strict sequence, it struggled to maintain context over long distances. By the time a computer reached the end of a complex frame or a long paragraph, it had effectively lost the big picture of how the beginning related to the end. Graphics engineers broke this bottleneck with a shortcut called reverse ray tracing. Instead of trying to calculate every light particle from the sun, most of which the camera never sees, they flipped the physics. They started at the lens, shooting virtual rays backward, calculating only the paths that contribute to the final image. In 2017, AI researchers introduced the transformer model, which performed a nearly identical shift. It abandoned the old sequential walking method entirely. Instead of reading one word at a time, the transformer looks at every word in a sentence simultaneously. To determine how they relate, it treats those words as coordinates in a geometric space and shoots out semantic rays in parallel to find connections. This means the AI revolution wasn't driven by a new understanding of human grammar. It was driven by the discovery that the most efficient way to process a sentence is to use the same spatial geometric logic that makes a virtual sunset look real. This mechanism is called self-attention. To calculate how words relate to one another, the AI assigns every word 3 distinct roles: a query, a key, and a value. As this diagram shows, these roles map directly onto the physics of a 3D scene. The query, or Q, is the active word asking a question, like the word chased, asking who did the chasing. It functions exactly like the camera pixel on the left, which shoots a ray into the scene to ask, what light am I seeing? As the ray travels, it looks for keys. In a sentence, the key is the surrounding words advertising their properties. In graphics, this is the 3D geometry of the room advertising its position, so the ray knows where a collision occurs. Finally, we have the value. Once the ray hits a surface, it collects the material color and light data. In an AI, the semantic ray collects the unrefined meaning of the target word and brings it back to the original word to provide context. By using queries, keys, and values, the AI translates a flat string of text into a physical environment that can be navigated and measured. This translation is visible in the attention equation. The math to determine if 2 words relate is identical to a ray tracing shader testing a collision. It starts with a dot product, which multiplies the query by the key. In graphics, this is the geometric test used to see if a ray is aligned with a target surface. If the vectors align, you have a hit. In the AI, the word ran structurally collides with the word marathon because their mathematical coordinates are aligned. However, it passes straight through the word the because their angles don't match. These collision scores are then processed by a softmax function. Because a surface cannot reflect more than 100% of the light hitting it, the softmax function acts as a material shader. It compresses the scores into a percentage. The word ran might decide to allocate 85% of its focus to marathon and 15% to athlete. The AI calculates these mathematical angles of relevance to distribute focus, in the same way a graphics engine distributes light across a room. But there is a scaling problem. Testing every single ray against millions of triangles or hundreds of thousands of words would crash a computer. Graphics cards solve this using bounding volume hierarchies, invisible, nested boxes that wrap around 3D objects. If a ray misses the large box containing a digital castle, the GPU instantly ignores the millions of triangles inside it. AI models use the exact same spatial trick. They cluster similar concepts into semantic bounding boxes. The concept of marathon is kept in an athletics box. When the query ray for ran is shot, the math instantly ignores the tax code or medicine boxes because their coordinates are completely misaligned. Organizing data into these nested spatial clusters is the only way to navigate massive amounts of information, whether it's light or language, in real time. In a ray tracer, a single light bounce provides only harsh, direct illumination. Realism requires a higher trace depth, allowing light to bounce off a mirror, through a glass, and onto a table. In an AI, transformer layers are the mathematical equivalent of those light bounces. As we see in this table, the more layers you add, the more complex the interactions become. At layer 1, a single bounce only resolves direct grammar, like matching blue to sky. By layer 12, the light of the sentence has bounced enough times to resolve a pronoun across a long paragraph. By layer 80, the context has ricocheted through the network so many times that the AI can resolve subtle metaphors or identify security flaws in a complex line of code. The intelligence we see in modern AI is the emergent result of allowing semantic light to bounce and mix across dozens of geometric layers. But there is a final physics problem. In the real world, materials absorb energy. If light bounced 80 times without energy loss, the scene would explode into blinding infinite white light. Deep AI models face the same threat. As word vectors pass through 80 layers of math, the original meaning of your prompt can degrade into random noise or expand into infinite numbers, causing the AI to forget your instructions. To fix this, transformers use residual connections. They mathematically add the output of a layer back to its original input. This blending of the new context with the base word is the mathematical counterpart to energy conservation. It ensures the original prompt is never lost, even after 80 bounces through the network. Modern AI functions as a high-dimensional virtual camera, shooting mathematical rays into the sum of human knowledge. It proves that whether we are simulating a sunset or a conversation, the universe is navigated using the same principles of coordinates, intersection, and light.